In this video, I'd like to talk a little bit about how we solve some limits with L'Hopital's rule when we have one of the indeterminate forms that's exponential. Now, let's take a look at this first one here. If I were to just plug 0 in, I get sine of 0 to the 0, which is a 0 to the 0 case, which is an indeterminate form. Let's see why that is. What we're going to do is, call this L, because what I'm going to do is actually take the natural log of what I got going on in here. So I got the limit as x goes to 0 of tangent x ln of sine x. Okay, so I'm no longer solving for L, I'm actually going to solve for the ln of L. We're going to take the limit of this guy, because notice what happens now. I have a 0 times infinity case, and as we've seen in the past, those can be turned into our version of L'Hopital's rule. So what we're going to do is put 1 over tangent x in the denominator, and let's go ahead and see what we can get to have happen. So limit as x goes to 0, and we're going to rewrite this as ln of sine x all over cotangent x. And there's now our infinity over infinity case. So applying L'Hopital's and recalculating the limit, we get limit as x goes to 0. And I'm going to have on top 1 over sine x, and the derivative of cotangent is negative cotangent x cosecant x. Sorry, wrong derivative. Derivative of cotangent x is negative cosecant squared x. So coming back over here, let's see what we got. Again, we simplify before we make any rash decisions. So I've got 1 over sine x over negative cosecant is 1 over sine squared x. And I got to go back because I made a small mistake. Derivative of ln of sine x, 1 over sine x times cosine x. I forgot that, I'm sorry. Jeez. Cosine x. So we're going to flip this guy and multiply it. So get the limit as x goes to 0 of cosine x sine squared x all over sine x. Cancel out one of those with the denominator. We can now plug and calculate the limit, because we have 0 cosine of 0 times cosine of 0, which is 1 times 0 or 0. Now what we have is that the natural log of L equals 0, therefore L equals e to the 0 or 1. And so there's one example. I want to do one more. One thing people forget, and they do a good job on these, and they forget to switch it back at the end. The other one we're going to look at is 1 plus 2x to the 1 over 2 ln of x. You get some practice at these. They get real easy, even though some of the stuff may look tough. So 1 over 2 ln of x ln of 1 plus 2x. And I apologize, we should probably make sure that what we have is L'Hopital's, because we're actually going to take a limit here as x goes to infinity. And so what I have is an infinity to the 0 case. Now here's why that is an indeterminate form, or can be made into one. If you look at what's going to happen here, this guy's going to go to infinity, this guy's going to go to infinity, and 0 right now. So right now it's a 0 times infinity. So what I want to do is write them over top of each other. ln of 1 plus 2x over 2 ln x. It's clear cut. infinity over infinity case. So using L'Hopital's, I get the limit as x goes to infinity of 1 over 1 plus 2x, that's the derivative of the top almost, by chain rule times 2. Can't forget the chain rule twice. That's just going to be 2 over x. I am going to flip this guy and multiply. So I have the limit as x goes to infinity of, I'm going to have x over 2 over 1 plus 2x times 2. Those 2's will nicely cancel out for us. So I get the limit as x goes to infinity of x over 1 plus 2x. This is basically an infinity over infinity case again. So applying L'Hopital's rule one more time, I get the limit as x goes to infinity of 1 over 2, which is 1/2. Now remember, this is not the limit. This is the natural log of the limit, so L equals e to the 1/2, or the square root of e. So, there's a couple of limits involving exponents.